Good morning, everyone. In today's class, right, we'll be seeing the last part of the design for the transform, that is the design of the windings. Okay, so here we have few basic steps. Okay, in the beginning, and then we'll go for the particular values for different windings, right, for on what it depends, etc. Right, so first one, you have number of turns, that is very much important, right? So windings, right? So in primary turns, that is if you note it as the number of turns in primary to be TP, then it will be voltage of the primary winding, okay, divided by voltage per turn, okay? So VP by ET, right? So we get VP by V by T, right? So we get the turns. Similarly for secondary, right, that is the number of turns in the secondary winding. TS is equal to the secondary voltage divided by the number of turns per, number of voltage per turn. Right, so ET, right, so we know that the turns in the primary, that is voltage per turn in the primary will be equal to voltage per turn in the secondary. Very much important. Okay. The next one, that is the number of turns on the LV winding. Okay, so it is usually determined, okay, making a small adjustment in the design, okay, to see that the voltage per turn, okay, we get, that is in the LV winding, that is the voltage per turn, we get it to be an integer. Okay, so with that, right, we with small modifications we go for the derivation, okay, that is the designing. So TLV, okay, that is turn in the LV winding, right? So it is such that the voltage, that is the LV voltage by the number of turns, is an integer. Similarly, to know the number of turns on the HV side, so THV is equal to VHV divided by VLV, right, into TLV. Okay, so that is the relation that we have. Okay, and the next one is we also have the tappings, right? So when we are having tappings, right, so we'll have more number of locations where we are deriving the voltage, right? So the one care must be taken here is, right, so that the number of turns that are there, right, between the taps, they must be of symmetry, right? That is very much important. That is the turns, right, is number of turns between the taps, they have to be symmetrical. Next one is the current in the primary winding, right? So that is IP is equal to, right, so here we will be making use of the power equation, that is we know kVA, that is, or VA, which is I into V, right? So from that we are getting the voltage, so the current. So IP is equal to kVA per phase, okay, per phase into 10 raised to 3 divided by the voltage, right? So that is what we get the primary current, right? So kVA per phase into 10 raised to 3 divided by the voltage in the primary. So once we get IP, right, we can calculate IS, right? So IS is determined by the relation, right, IS by IP is equal to VP by VS, right? So that is what we are making. Therefore IS will be equal to IP into VP by VS, right? So here you can see that the voltage ratios and the current ratios, right, so they are inversely proportional. That is, or you can, the other way you can say that the voltage in the primary and the voltage in secondary, right, and the current in the primary and the current in secondary, they are inversely proportional. That's what we can know, since the power is constant. Okay, there will be no change in the power. Therefore VP IP will be equal to VS IS. On that basis, the increase in the voltage from primary to secondary will reduce the current, right, and the vice versa also, right. Next important is the area of conductors that we are using for the windings, right. So here the important factor which has to be considered here is the current density, right. So we know current density is the ampere per area, okay, so ampere per area, right. So that is what we'll be taking into consideration, or that is the important factor that it is to be considered when we are finalizing the area of the conductors, right, or you can say the area of the windings, right. So why it is so is right. So what the significance of current density is this, right. So the current density, right, so once we know the current density, right, so we'll be able to design, right. So the current density should be what it is allowed by, that is means what are the factors on which the current density is dependent, or you can say the factors affecting the current density, the local heating, okay. So the local heating, right, and the efficiency, right, that is when I say efficiency, it will be due to the losses, right. So next we have is, right, the temperature rise, right. So if the temperature rise is more, right, so what does that means? It is possible, right, when we have high current density, right. So at higher current density, right, so the temperature rise will be more. So what this is going to lead is, or what is the effect of having high temperature rise is that there will be failure of the insulation, because of more current density, right. So more the temperature rise, right, so which will lead to the insulation failure, right. So all this should be, this is the current density and the temperature rise, they all have to be within the permissible limit, right. So if they are not within the permissible limit, that is the current density, which will lead to the temperature rise, that is the higher the current density, higher the temperature, which will ultimately lead to the failure of the insulation. Therefore current density chosen, that is chosen, right, while we are designing the area of conductors must be very good value. The choice of current density is very important, right. So as we have discussed just now, right. So and also, right, this current density, right, so whatever is the current density, that will also decide, right, the I square R losses, right. So the I square R losses and the loading for maximum efficiency, right, these 2 points, that is the I square R losses and the loading for maximum efficiency, this both are controlled by the current density, right. So next is current density in a winding depends level of losses and cooling system, that is what, right. So even in the starting limitations we have just gone through them in a different way, right. So if you have a better cooling system, right, so then we can see that more current will be flowing through the system, so that the losses that take places due to that current, right, so the heat will be effectively cooled faster or it will the temperature will reduce before it is going to have any adverse effect. That is what this point is telling, that is the current density is in a winding depends on the level of losses and cooling systems, right. So if you have a better cooling system, right, so we can have the current density high, okay. The next one is the level of losses, okay. This is as we know, they are different for different types of transformers, right. So here the type of transformer means, right, they are the power transformer and the distribution transformer on the basis of their application, right. So they, for power transformer the losses, right, they are different, and for the power and distribution transformer, since the losses are different, right. So as we have already in the previous point noted that the current density is dependent on the losses. Since the losses are different, therefore the current density also for the power and distribution transformer will be different, okay. So below we'll see few lists, right, or values that are there, okay. So for different type of transformer, what up to what level of current density we can use, okay. So for distribution, small and medium power transformer, that is here for distribution type, small and medium power transformer means again it depends on the kVA rating, right. So for distribution transformer and small and medium power transformers which are self oil cooled, okay. So normally they are oil cooled, right, and up to 50 kVA, that is the power rating, right? So up to 50 kVA, right? The current density that is safe to work with is between 1.1 to 2.3 ampere per meter square. So this will be the current density, right? Or you can call that is, these are the limitations for the current density for such type of transformers. Okay, next one we have for large power transformer, self oil cooled, right, or air blast. Okay, so if the cooling is through oil or through the air, okay, so it is the value of current density, it can lie between 2.2 to 3.2 ampere per meter square. Okay, so since here we can see it, right, the cooling systems are different from the first and the second, right? So first it was only oil cooled, right? So here we have the air blast, that is we are forcibly also using the forced system of cooling. Okay, so therefore the current density values are high compared to the first one. And similarly for large power transformer with forced circulation of oil or with water cooling, right, so the value of current density, right, so here it is very high, the comparatively 5.4 to 6.2 ampere per meter square. Okay, so again because of the cooling here, right, so we can go for the value of current density up to 5.4 to 6.2 ampere per meter square. Okay, so three different we have seen, one for distribution transformer, okay, and with small and medium power transformer, right. The second one is large power transformer with type of cooling, and here again it is for large power transformer with more better cooling systems, right. So for these three cases we have seen the values of the current density. In the next part we will see the, right, the condition, right, so for minimum losses, okay, with respect to current density, that we'll see now. Condition for minimum losses, that is I square R losses with respect to current density, right. So what we have is the derivation, a small derivation, right, area of each primary conductor AP, right, that is IP by delta P, because delta is current per area, right, so that is the current density, so area is current by delta. Similarly for secondary conductors, okay, the area is AS, which is IS by delta S, right. So next we are assuming UP and US, right, these are nothing but the volume, okay, volume of conductors in primary and secondary windings respectively, right. So these are the volumes, right, and we have UT, that is the total volume of conductors, right. So total, that is the summation of the primary volume of the conductor UP plus the volume of the secondary conductor, so UP plus US, right, so which is UT. And next assumption that we have here is, right, the total volume of the conductor, that is UT, is constant. So this is the assumption, that is the total volume of conductors, right, which includes the volume of the conductor in primary and also the conductor or volume of the conductor in secondary to be constant, right. So the losses in the primary, right, that is I square R losses, which is given by rho, this is the current density square into the volume, right. So how do we get this is, right, we have I square R, okay, so two different, so I already we have, that is the equation that we have, right. So now we will be considering with respect to the current density, so delta is equal to ampere or I by area, okay, so that is what we are using. So I will be equal to area into delta, okay, so the square of this into R, we have R is taken by the basic equation, that is rho L by A, okay, that is how it is. Then so A here is the primary, okay, so therefore it will be AP square and then delta P square into rho L, that is the length of the primary conductor, divided by AP, since it is the conductor of the primary. So this and this will get cancelled. Okay, so the remaining what we have is rho, right? So rho as it is, this length into area, which will give the volume UP, and delta P square. Okay, that is what we have here, rho delta P square into UP. Okay, that is how we are getting it from the basic equations. Okay, similarly the losses in the second winding is rho delta delta S square US, similarly from this fashion, right? So we'll be just substituting the S in places of P, that is the secondary in places of the primary. So what we are having is here US, right? We had UT, which was equal to UP plus US. So now US will be UT minus UP, that is what it is substituted here. Okay, and then total losses. Okay, I square losses from basic we have as the losses in the primary plus losses in the secondary. That is what is done in the primary. It was rho delta square P UP plus rho delta S square UT minus UP, right? So that is what is taken here, right? And then the equation PC is differentiated with respect to UP. So delta PC by delta UP, which is equal to this much. Okay, so this is a constant which is outside, right? So this, right, so is the differentiation of UP with respect to UP will be 1, that is what it is. So delta P square as it is, plus, right, so here, right, so what we can have is delta S square UT minus delta S UP, right? So we are having this as a constant. Okay, so delta S into UT will become 0, and delta S square UP, differentiation of UP with respect to UP is 1, so we get delta S square. Okay, this is the differentiated equation of PC with respect to UP. Okay, next we are having for minimum losses. So usually we equate the differentiated equation with to 0, that is what is same is done here. Right, okay, so rho delta P square minus delta S square will be 0, right? So when we get that is delta P is equal to delta S. So that is the current density in the primary is equal to current density in the secondary. So it is, so for minimum losses, that is I square losses, the value of current density in each of the two windings, that is in the primary and secondary, should be equal. So when we have this condition, that is delta P is equal to delta S, then we have the minimum I square R losses. Okay. And one point to note down here, right? So usually we said that delta P is equal to delta S, but practically, right? So the current density of the outer winding, right? So usually how it is, right? We have a core, right? So we'll have one winding, right, and above that we'll have one more winding, right? So this is how the practical arrangement is made, right? So the one winding and above. So the outer winding, right, is usually 5% more than the inner winding. So this is done, right? So because the outer, right, compared to the inner windings, the outer windings are having better cooling system, right? So because here it is easy for them to dissipate the heat that is generated, therefore so this outer will have 5% more with respect to, that is the current density, the delta value that I can say is, right, if I take delta, right, outer, right, and delta inner, right, so this delta outer is greater than delta inner, right, by how much? By 5%. That is what is the practically done, and this is possible because of the cooling, that is the, since the heat dissipated here, it is better in outer winding compared to the inner winding. Okay, in the next part, right, so we'll go for selection of type of windings. Okay, so different So different types of winding, right? So here again it depends on the process, that is the applications. Okay, so different windings, right? So the main thing when we are designing the winding, right? So what is the most important thing that we should consider here is, right, it should meet, right, the desired electrical characteristics, and it should be also able to withstand mechanical stresses. That is what we have seen even in the limitations, right, in the beginning also, right? So mechanical limitations we had, right? Same way here, right? So the design, we should take care of both the electrical characteristics and also the mechanical characteristics. Here the mechanical is nothing but the stress, right? So whenever we have the mechanical forces that are acting on conductors, they should be able to withstand those also, right? And with the basic requirement of meeting the electrical characteristics. Right, so we are having type of windings, right? So for different purposes or applications, right? So for high voltage windings, okay, so for voltages at higher end, right? So we have three different types, okay? Cylindrical winding with circular conductors, crossover windings with either circular or small rectangular conductors, and third one is continuous disc type winding, okay, with rectangular conductors. So for high voltage windings we have these three types, that is cylindrical winding, crossover winding, and disc type winding. So where and all we'll be making use of this, we'll see, right? The cylindrical and the crossover, okay, so they are where, right, for 1000 kVA and 33 kV, that is the voltage, right? So for such we go for cylindrical and crossover windings, and this type is used, okay, so where we have the requirement, that is from 200 kVA to tens of MVA, like, right? So 10, 20 MVA, 30 MVA, up to that, right? And the voltage here is above 11 kV volt, okay, so above 11 kV volt we'll go for the disc type windings. And then for low voltage windings we have two types, cylindrical and winding and helical winding, right? So here both are making use of the rectangular conductors only, okay, fine. So we have this, right? So the cylindrical, that is cylindrical, will be making use it up to 800 kVA, okay, so 800 kVA and 433 volt, okay, so 800 kVA and 433 volt. And then the helical, okay, the helical winding, right, up to tens of MVA, right, up to 15 kV voltage, or sometimes up to 33 kV voltage. And then we have one more winding, that is the sandwich winding, right? So these windings, right, they are used in the shell type transformer. We know that where we have the primary and secondary sandwiched, right? So one below one, another the other, okay. So the sandwich windings are for transformers where it is of shell type, right? So to end this topic, right, so we have a table here, right, so where we have the relation, that is what type of winding can be used, right? So for watt rating, that is the kVA, voltage kilovolts, okay, and maximum current per conductor, right? And then we have conductor cross section, right, that is the area, okay, and number of conductors in parallel, okay. So for cylindrical winding with circular conductors, right, so kVA rating is up to 5000 to 10,000, okay, the voltage you can go up to 33 kV, right, and maximum current that is per conductor is up to 80 ampere, right, and then conductor cross section up to 30 mm square, okay, so and number of conductors in parallel is 1 to 2 conductors per parallel path, okay. Next we have is cylindrical or rectangular. Cylindrical with rectangular conductors, okay, cylindrical winding with rectangular conductors, so it will go up to 5000 kVA to 8000 kVA, up to 6 kilovolt. Okay, and then current per conductor, the range is 10 to 600 ampere. Okay, the area is 5 to 200 mm square, and number of conductors in parallel is 1 to 4. And similarly for the crossover, okay, crossover we can go up to 1000 kVA, right, and up to 33 kilovolt, right, and then current per conductor up to 40, right, and then the cross section area, that is up to 15 mm square, and number of conductors connected in parallel will be 1 here. Next one is helical, right? So for helical we can go somewhere from 160, right, kVA to tens of thousands of kVA. Okay, fine. And the voltage here is, that is what, up to 15 kVA or up to 33 kVA. Okay, so the maximum current per conductor, right, so from it starts for 300 and above those value, above 300 ampere per conductor. And then we have a cross section, right, so here it will be 75 to 100 mm in square, okay, and above, right, so for, and then the conductors in parallel, right, so it is 4 to 16 conductors in parallel, right, so in the bracket it is more, right, so you can even have more depending on the necessity. And the last one is continuous disk, that is from 200 to tens of thousand. Okay, so it is 3.3 kV to 220 kV. Okay, and then maximum current per conductor, right, so 12 ampere and above. Okay, and then the cross section area, that is from 4 mm square to 200 mm square and above, and number of conductors in parallel is 1 to 4. Okay, or as per requirement more than that, right. So this is the part that we will be having in design of windings. Thank you.